we have looked at the notion of the orthogonal complement of a subspace in R k. Orthogonal complement of a subspace W of R k. And then we use the properties of this orthogonal complement in the case of the matrix situation. And in the matrix situation, we have a matrix A, which is an m by n matrix real, and we have on the for R n we have two subspaces, namely the range of A transpose and the null space of A, and for R m we have the two subspaces, the range of A and the null space of A transpose. We observed that these two pairs of subspaces are orthogonal to each other. So, we had the null space of A is the R A transpose perpendicular, and hence the null space of A perp is R A transpose, and similarly on the R m side the null space of A transpose is the range of A perpendicular, and the null space of A transpose perpendicular is R A. We then used the notion that the dimension of any subspace plus its orthogonal complement is the whole space. So, dimension of R A plus dimension of R A transpose perp. So, the dimension of R A transpose plus the dimension of R A transpose perp, since both are subspaces of R n, must be equal to the dimension of R n, which gave us this is the rank of A transpose, and since R A transpose perpendicular is equal to N A, this dimension is the same as dimension N A, which is the nullity, and that was equal to n. And by rank nullity theorem, we had rho A plus nu A equal to n. These two together gave us that rho A equal to rho A transpose. Therefore, the rank of a matrix is equal to its transpose. So, the rank of a matrix is equal to rank of its transpose. This is the first important thing that we observed. Therefore, we had on the R n side the two orthogonal subspaces, each being orthogonal complement of the other. On the R m side, we had this null space of A transpose and the range of A, and again these two pairs of subspaces are orthogonal to each other, and the dimension of this and the dimension of this are the same, because the rank of A is rank of A transpose we found, and now we will denote by the common dimension as rho. So, rho is the rank of A. From now on we will not write rho sub A, because rho sub A is the same as rho sub A transpose. The dimension here is nu A and the dimension here is nu A transpose. As we mentioned in the last lecture, our basic aim will be to find orthonormal basis to the 4 subspaces in such a manner that it helps our problem of analyzing the matrix. We shall now look at one more property of the subspace, that is what is known as the best approximation from a subspace. The best approximation from a subspace. So, what do we mean by best approximation? So, we have the space R k, and in that we have a subspace W, and let us say W is a subspace of dimension D in R K. So, we have a subspace of dimension D in R K, and now what we are going to do is we look at a vector x which is outside W, it may be inside W, but we take a general vector x in R K. Now, what we would like to do is try to approximate this vector x with a vector W in W. So, if we take any W in W and consider it as an approximation of x, then the error is quantified. We wanted x, we have approximated by W. So, there is going to be an error, and that error is going to be quantified by the square of the length of the difference vector. So, we wanted x, we are approximating it at W. So, the error vector is x minus W, this is called the square error. Okay. This is called the square error. The square error is the length of the error vector squared. Then the error we get is this. We would like to minimize this error. So, we would like to minimize this error. What do we mean by this? This means we want a W naught in W such that if we now take W naught as the approximant and calculate the error, this is the error that is got by taking W naught as the approximation of x. Now, I look at the error I get by taking any other W naught, that will be x minus W squared. This must be strictly less than this for every W in W, W naught equal to W naught. This means, if you take the vector W naught and calculate the error is going to be smaller than by taking any other vector as the approximant for x, and hence W naught becomes the best approximation with the mean square, with the square of the error being least. So, that is called the least square approximation. Okay. Does there exist such a W naught? Obviously, the way we have stated, it means the W naught is unique, because the moment you pick W naught, every other W is going to get more error. So, we are expecting that there will be a single vector W naught which will approximate it. So, we would like to know whether there exists such a W naught. Let us investigate this question. Now, W is of dimension D, and therefore, we can find an orthonormal basis, and how many vectors will it contain? It will contain exactly D vectors. So, let phi 1, phi 2, phi D be an orthonormal basis for W. So, now we have the D dimensional space W, and we have found an orthonormal basis. Now, if we take W, any vector in W, so any vector W in W can be expressed as a linear combination of phi 1, phi 2, phi D, because phi 1, phi 2, phi D is a basis for W, can be expressed as a linear combination of W phi 1, phi 2, phi D as W equal to say alpha 1 phi 1 plus alpha 2 phi 2 plus alpha d phi d. And therefore, the error will be square error x minus w squared. The length of the vector square is the dot product of x minus w with itself. The length of any vector square is the dot product of the vector with itself or the inner product or whichever way we want to call it. So, which is the same as the dot product of the vector alpha 1 alpha d phi d with the same vector So, this is the inner product. Now, we know that the dot product is distributive, we can take term by term inner product. So, the first one gives me x comma x, the second one gives me minus alpha 1 x comma phi 1 minus alpha 2 x comma phi 2 and so on minus alpha k x comma phi k. Then we get another from here minus alpha 1, taking these terms again we get minus alpha 1 x comma phi 1, we get phi 1 comma x 1, but since we are in the real space the dot product is commutative, x dot u is the same as u dot x. So, again we can write it as x comma phi 1, x comma phi 2 and x comma phi d. Then finally, we get the cross products of alphas. Since phi's are orthonormal, the phi I phi j terms will go and the phi I terms will give 1. So, I will get plus alpha 1 squared plus alpha 2 squared plus alpha d squared. We will write this in summation notation. X comma x is first of all the length of squared and this remaining thing can be written as summation j equal to 1 to d alpha j squared, that takes care of the square terms, minus 2 alpha j x phi j, that takes care of the remaining terms. So, we have this. Now, therefore, the square of the error, if I take any vector w in W and calculate the square of the error, and the square of the error turns out to be this. We will make a simplification, we will complete the square inside the sum. We have alpha j squared minus 2 alpha j x phi j, which is of the form a squared minus 2 a b. So, if we add b squared and subtract b squared in order to complete the square, this is now equal to plus summation j equal to 1 to d alpha j minus x phi j, the quantity squared, minus that extra thing which we added, we now subtracted x phi j square. Now, therefore, for any w equal to alpha 1 phi 1 plus alpha d phi d in W, the square error is norm x minus w squared, the length squared, is equal to the length of x squared plus j equal to 1 to d alpha j minus x phi j squared minus summa j equal to 1 to infinity x phi j squared. Now, we are trying to minimize the error. When we are saying that we are minimizing the error, this means we are minimizing the right hand side. We are minimizing the right hand side, well, the vector x is given, we can do nothing about it, and the orthonormal set in W is fixed. So, we can do nothing about it. We are trying to minimize it by choosing the suitable vector in W. By choosing a suitable vector in W, we mean suitable values for alpha 1, alpha 2 and alpha d. This means we have to adjust the alphas in such a way the right hand side becomes minimum. The alphas appear in the middle term. Now, if we want to make it minimum, this is the sum of squares So, each term is non-negative. So, the best way to make it minimal is by making each term 0. So, the error, the square error is minimum, the square error is minimum when alpha j is equal to x phi j. If any one of the alpha j's is not equal to x phi j, then there will be an additional contribution from the middle term and therefore, the error will increase. Hence, if we choose w naught to be equal to, by choosing these values of alpha 1, alpha 2, alpha d, we get x phi 1 phi 1 plus x phi 2 phi 2 plus x phi d phi d, then we get the error is obtained exactly as norm x squared minus summation j equal to 1 to d x phi j squared, and this is strictly less than norm x squared plus summation j equal to 1 to d alpha j minus x phi j squared minus summation j equal to 1 to d x phi j squared, for which is the same as this quantity is norm x minus w squared for any other w in W, and therefore, w naught is the vector that gives the least error. Hence, w naught equal to summation j equal to 1 to d x phi j belongs to W and approximates x from W with least error, least square error. This is called the best approximation. This is called the best approximation of x from W. We are going to make a few observations now. So, what we have got so far is, if you start with a vector space with the vector space R k, and then you look at this is the vector space R k, inside that vector space is the subspace W, and we are looking for any given vector x in R k, a vector inside W which approximates it with the least error, least square error, and we have now found that least square error approximation is given by this vector W naught. Now, we are going to make certain observations. You recall that the right hand side of W naught, the vector W naught has been defined to be this, and if you recall, this is precisely the orthogonal projection of x onto W. So, note W naught is equal to j equal to 1 to d x phi j is equal to x w, the orthogonal projection, of x onto W. Therefore, the orthogonal projection is the best approximate. So, therefore, the best approximation of x from W is the orthogonal projection x w of x onto W. Similarly, the orthogonal projection of x onto W perp is the best approximant of x from W perp. Okay. Similarly, x W perp is the best approximant of x from W perp. Notice that if we know that x W, we also know x W perp, because x W plus x W perp is x, and therefore, if we know one of the two approximants, we automatically know the other approximants also. So, therefore, we know how to get this best approximation. What is this least error? The least error that we get is given by the error that we get by taking W naught as the approximation, which is norm x squared minus j equal to 1 to dx by j square. So, the least error is least square error is equal to summation j equal to 1 to d x by j squared. If we now look at the error, this is W naught x minus, let us do this a little bit more carefully. Let us first find what is, we have x is equal to x W plus x W perp, and therefore, the best approximant we have seen from W is x W. Therefore, least square error is equal to x minus x W squared, but Pythagoras theorem told us that x W squared plus x W perp square in norm is equal to the norm of x squared. So, this is equal to norm x W perp squared, since by very because x minus W is equal to x W perp. So, we have the least the error is the projection onto the other orthogonal complement. So, if you take W, and if you take x, and if you look at x W, and this will be the best approximation of x onto W, and what is the error? The error is the remaining part of x, which is x W perp. This is the error vector, and therefore, the length is the square is the error square. So, the error is given by the length of the orthogonal complement, and the approximant is the original vector. Let us look at one simple example. Let us take R 3. So, in R 3, consider the subspace which we have seen before, the subspace consisting of all vectors A, that means these are vectors all of whose components are equal. First component is A, second component is A, and third component is A. So, we have this subspace, we already seen that this is a subspace. Now, suppose we take, so let x be any vector in R 3. So, we want to find best approximation of x from W. So, what we have learned so far says that in order to find the best approximation, you have to look at the orthogonal projection. So, we know this is given by the orthogonal projection of x onto W. We have seen in the earlier lectures that the orthogonal complement in this situation is exactly given by, we have seen So, we see early lectures, previous lecture, that so the earlier lectures we have seen that the orthogonal projection x w is precisely x 1 plus x 2 plus x 3 by 3, x 1 plus x 2 plus x 3 by 3, x 1 plus x 2 plus x 3 by 3. So, the vector which approximates x best from w is given by taking the average of all the components. So, we have the vector x is equal to x 1, x 2, x 3, w wants all components to be equal. So, we want to construct a vector from x where all components are equal with least error. The best thing is to take all the components to be the average of the components of x, and we have x 1 plus x 2 plus x 3 by 3, x 1 plus x 2 plus x 3 by 3 and so on. Now, let us verify this directly. Let us verify this directly. What do we mean by this? Take any w in w. Now, any vector in w has all components equal. So, let w be equal to t t t, where t is a real number. Now, what is the square error? The square error is the difference times the length. Now, what is the length of the vector? What is the difference vector? X is the vector x 1, x 2, x 3, y the w is the vector t t t. So, it is going to be equal to x 1 minus t, x 2 minus t, x 3 minus t, this vector square. But the length of the vector square is the sum of the components squared. So, it is x 1 minus t squared plus x 2 minus t squared plus x 3 minus t squared. Now, we want to find that vector which minimizes this error. That means, we want to find the value of t for which this is minimum. Okay. So, we want to find w such that this square error is minimum. That is, we want to find t in R such that the error square was x 1 minus t squared, x 2 minus t whole squared, x 3 minus t quantity squared is minimum. So, we are given the vector x, and therefore, x 1, x 2, x 3 are fixed. So, we have to treat this as a function of t. We have a function of t and we are trying to find the minimum. In calculus, we have learned that to find the minimum, first find the places where the derivatives vanish, that is called the critical points, and decide if at a critical point if the second derivative is negative, it is maximum, and it is second derivative is positive, it is a point of minimum. So, let us call this as the E t, the error function depending on t, what vector you choose. So, this is E t, and we are trying to minimize this function. Therefore, we differentiate this function with respect to t, and we get minus 2 x 1 minus t minus 2 x 2 minus t minus 2 x 3 minus t, which is equal to, there is a 2 t, there is a 2 t, there is a 2 t. So, there is a 6 t minus twice x 1 plus x 2 plus x 3, and therefore, the derivative is 0 when t is equal to x 1 plus x 2 plus x 3 by 3. If we accept this equal to 0, we get t is equal to x 1 plus x 2 plus x 3. So, there is only one critical point which is t is equal to x 1 plus x 2 plus x 3, and if we see that d squared e by dt squared is just 6, it is always positive, and therefore, if we have a critical point and the second derivative is positive, and therefore, this is always 6, and therefore, d squared e by dt squared when t is equal to x 1 plus x 2 plus x 3 by 3 is also 6 greater than 0, and therefore, t is equal to x 1 plus x 2 plus x 3 by 3 is the point at which E t is minimum, and the vector corresponding to that. Therefore, the vector w in W corresponding to this t is x 1 plus x 2 plus x 3 by 3, x 1 plus x 2 plus x 3 by 3, because we have t all components as t. Now, we have found the t value as this, and this was equal to x w as found earlier. So, thus we find that the best approximation is indeed the projection of x onto W. So, thus now we know how to approximate a vector from a subspace. Okay. Note, if x is in W, then he is himself its best approximation. If you project x onto W, you get x itself, then x w equal to x, and hence x is itself its best approximant from W naturally, because already in W. So, now we have learnt a lot of things about a subspace, its orthogonal complement, best approximation, etc. Let us now consolidate all these facts and see how we have interpreted them in the context of matrices. So, first we will divide into two parts, one in general vector space R k, and then we look at the matrix context, how we use these things in the matrix context. So, we take a matrix A which is an m by n matrix. So, we look at the general space R k. In the matrix context, we have to look at two such spaces R n and R m, because the matrix A converts R n vectors into R m vectors. So, we look at R n and R m. So, there are two spaces like this R k which are of interest on the matrix situation. Then we introduce the notion of a subspace in R k. Now, in the matrix context, we have two situations, again R n and R m. We had two subspaces in R n, two subspaces in R m. So, we have two subspaces the range of A transpose and the null space of A in R n, and B the two subspaces the range of A and the null space of A transpose in R m. So, that is the second thing that we observe, the notion of subspaces, how we use in the matrix context. Then we had the notion of orthogonal complement, W perp of a subspace W. We use this on the matrix context for these four subspaces that we have. So, we have R A transpose perp and N A perp in R n, and then we have R A perp and N A transpose perp in R. When we did that, we had a property of the fact that we observed that N A was R A transpose perpendicular and N A transpose was R A perp. We had this. Then we found that the perp of a perp is the original space. The orthogonal complement of the orthogonal complement is the original subspace W. When we use that in the matrix situation, we got that the R A transpose is N A perp and R A is N A transpose perp, and consequently using this along, then we had, okay, let us put this dimension of W plus dimension of W perp was equal to k. When we use that here, we get the rank of A transpose plus the nullity of A is equal to n. But then this plus using together with rank nullity theorem gave us rho A equal to rho A transpose. That is, the rank of any matrix is equal to the rank of its transpose. We further have that if B W is a basis for W and B W perp is a basis for W perp, then B equal to B W perp union B W perp is a basis for R k. Now, if you use this notion in the two R n and R n spaces, for the matrix case we get if B R A transpose is a basis for range of A transpose and B R A transpose perp, but what was R A transpose perp, which was same as B N A. So, we will put it that way. So, that is B N A is a basis for R A transpose perp, which is equal to N A, then B N equal to B R A transpose union B N A is a basis for R n. Similarly, a basis for R A union a basis for N A transpose equal to B a basis for R m. Let me put it as B m. So, we have got this basis concept and correspondingly orthonormal basis. So, we have orthonormal basis for W union orthonormal basis for W perp is equal to orthonormal basis for R k. If we now apply this to the matrix situations, orthonormal basis for range of A transpose union orthonormal basis for range of A transpose perp, which is N A, is equal to orthonormal basis for R n, and further we have orthonormal basis for range of A union orthonormal basis for range of null space of A transpose is equal to orthonormal basis for R m. So, these notions of basis, orthonormal basis, decomposition, orthogonal decomposition, etc., we have now. Again, we found that x belongs to R k implies x is equal to x w plus x w perp, x w belongs to w, x w perp belongs to w perp, and this decomposition is unique. Any vector in R k can be decomposed as the sum of a vector in w and a vector in w perp. Now, we consolidate this here. On the R n side, we get x belongs to R n, x is equal to, we take w to be x in R A transpose plus x in R A transpose perp, R A transpose perp is N A, and this decomposition is unique. And on the R m side, if B belongs to R m, that implies B can be transposed decomposed as a part which is in R A, I am taking W as R A now, plus a part which is in R A perp, but R A perp we found was N A transpose. So, any vector in the n dimensional side can be decomposed as a vector in R A transpose and a vector in null space of A, and any vector in the m dimensional space can be decomposed as a vector in the R A and a vector in N A transpose, and these decompositions are unique. And then finally, today we learned that the best approximation. So, the best approximation of x from W is x W. So, if we now extend use this idea in the matrix situation with the spaces, in place of W we will use R A transpose once and R A on the other side once. So, the best approximation of x from R A transpose is the projection of x to R A transpose. Best approximation of x from R A is the projection of x in R A, and this x, this is the R m side and this is the R n side. So, any vector in R n can be approximated with least square error from R A transpose, and any vector in R m can be approximated with the least square error in R n. And then what is the least error? Is the norm of x w perp squared. So, in this, in the A case, that is when we are approximating vectors in R n by vectors in R A transpose, the least square error is the projection of x into N A and that squared, because R A perp, R A transpose perp is N A, and similarly in the R m side the least square error is norm of x N A transpose square. So, all these notions we have studied so far have their role to play in the matrix situation with respect to these 4 subspaces that we have seen. We repeatedly assert the fact that these 4 subspaces are going to play a very major part in our analysis. Now, we have consolidated a lot of information about these 4 subspaces, how to deal with them. We have realized that they split, R n for example is split into 2 parts, but by R A transpose and N A, and R m is split into 2 parts by R A and N A transpose, and we have seen that the vectors can be split, they can be approximated with least error from both these spaces, and all these facts will be used. The basis can be put together to form a basis, orthonormal basis can be put together to form an orthonormal basis and so on. So, these are the facts that we will be repeatedly using. Now, the crucial part in all this is this, the orthonormal basis. We have seen that the orthonormal basis for W and an orthonormal basis for W per together gives me an orthonormal basis for R k. Similarly, therefore, if we now take the main part, again I repeat, the main part therefore is, if you now choose R n and you look at the matrix which gives the decomposition, we have this decomposition. The R n is split into R A transpose and N A, and the R m is split into the range of A and to N A transpose. This splitting is an orthogonal splitting, and therefore, any vector can be decomposed, and all these facts we have just seen before. So, now what we are looking for is the fact, if we now choose an orthonormal basis for this and an orthonormal basis for this, the two together, their union will give me an orthonormal basis for R n. Then an orthonormal basis for this and an orthonormal basis for this, the two together will give me a basis for R n. So, our main aim is to find these 4 orthonormal bases. The 4 orthonormal bases can be found, but we want to find them in such a way, we want to link them in such a way that using these linked bases we can assert the answers for all the questions about the matrices that we raised. So, the real strategy lies in the strategy for choosing this basis. We shall look at these strategies as we go along. The main, so this the hunt for suitable basis, we will explain as we go along what is suitable for us. We will look at the questions we have asked, and we will see which is the basis that makes the working easy for us, gives the answers in easy language, and those are the bases that are suitable for us. So, the hunt for suitable basis for these 4 subspaces leads us to the notion of eigenvalues and eigenvectors. So, therefore, this notion of eigenvalues and eigenvectors is a very important notion in matrix theory, and this has this role to play in the analysis of the structure of the matrix and the analysis of finding the various questions of the matrix. So, now we will soon see how they play this role, but before we do that, we shall look at another problem in which these notions of eigenvalues and eigenvectors play. So, another problem where eigenvalues and eigenvector notions appear, but this is the main problem in which it appears, from which we move on to the other question that we raised above. Notions appear. What is this problem? Now, let us again and again we should remember that the origin of linear algebra was in the analysis of systems of equations, linear systems of equations, and in the beginning we said we shall first study simple system. Among the simple systems in n equations with n unknowns were the simpler ones. So, what we did was we looked at a system A x equal to b, a non-homogeneous system. A was an n by n matrix and B was an n vector. We want to find x in R. What we said was we want change of variables, because we said that diagonal systems are easy. So, we want to change variables to bring it to a diagonal system. So, we said y equal to some changed x, z is equal to some changed b, where C is an n by n matrix and invertible. When we change these variables, we can write x as C inverse y, which we call as P y, b as C inverse z, which we call as P z. Then if you look at the system A x equal to b, now with the changed variables becomes A x equal to or P inverse A P y equal to z. If we can choose P such that P inverse A P is diagonal, then we have an easy system for y. We have a diagonal system for y, and therefore, we can analyze y, and once we analyze y, we know the information about x. So, therefore, the main question is, can we find a p such? So, can we find p such that P inverse A P is diagonal? This is the main problem which leads us to the notion of eigenvalues and eigenvectors. We shall see in the next lecture how such a question leads us to the notion of eigenvalues and eigenvectors, and how this notion of eigenvalues and eigenvectors play a crucial role in the answer to this question, and how these eigenvalues and eigenvectors appear in the formation of this hunting for these 4 suitable bases.